Hi everyone, can everyone hear me well? Yep. Okay, so it's a great pleasure to be here. I'm very excited that we have, for the second summer, I'm participating in this school as a lecturer. And yeah, surprisingly this time the talk is a bit different. So this time I will be talking about extending the reparameterization trick. It's something I've been working on for not really a while, like half a year, but I'm really interested in this topic, and I will mostly talk about other people's work, but also about mine. Okay, so I'll start from the basically last slide. I will tell you what you should learn from this lecture. And the first thing I want to point out is that the reparameterization trick is just one method for solving the problem of stochastic gradient estimation, which is a general and important problem which is considered both in machine learning and outside of machine learning. So reparameterization and reinforce are two main methods for this problem, but just having this broader perspective of that gives you some potential ideas on how you can combine them or transfer some ideas between them. And the second message is that reparameterization can be applied to almost any continuous distribution. So for most of the summer school, you mostly heard about using a normal distribution with reparameterization, but you can also use it with pretty much any continuous distribution, such as gamma, beta, Dirichlet, and von Mises. Okay, this is the outline of the talk. I will start with overview and will introduce the stochastic gradient estimation problem. I will review reinforce and reparameterization gradients, and then I will compare them and give you some intuition on when one is better than another. Then I will talk about how we can extend the applicability of reparameterization, and I will present two methods for that: generalized reparameterization gradients and implicit reparameterization gradients. And finally, I will discuss how we can reduce the variance of the reparameterization gradient. All right. In order to pose the problem of stochastic gradient estimation, we should first have a parametric continuous distribution Q phi of z. So I'm only going to talk about continuous distributions, not about discrete distributions. And I'm going to assume that this distribution is basically well behaved. But by that, I mean that, for example, the density is differentiable. So of course, you can easily construct continuous distributions with non-differentiable density. But if you think about the, like, for example, all the ones I've mentioned, they all have differentiable density. This distribution is going to be vector valued. So capital D is going to be the dimensionality of Z, the random variable. And phi is going to be a scalar parameter. If we have more than one parameter, we can just do this kind of estimation for every parameter, which is why it's still very general. Now, we suppose that we have a differentiable cost function f of z, and it's a scalar function. So it maps d-dimensional vectors to scalar values. And then we can introduce expected or mean cost L of phi, which is just the expectation of the cost over this distribution. And we basically want to either maximize or minimize it, but in order to do that, we first want to compute the gradient, the derivative with respect to phi, so that we can apply gradient-based methods. All right? And so our goal is to construct an unbiased stochastic estimator for this derivative. And by unbiased stochastic estimator, I just mean that basically this equation holds for this G, which we want to construct. If we have this G, then we can construct a Monte Carlo estimate of the gradient and use that in our favorite optimization methods, such as ADAM, for example. Ideally, we want this estimator to have low variance. Why is that? On Tuesday, we talked about stochastic optimization methods, and basically the variance of this estimator is the main thing which determines how fast the methods will converge. So depending on the variance, we can either wait for a model to train for 2 months or 1 day. It's a big difference. So we just want to reduce it as much as possible. There are many applications of these problems. Some of them you've seen during this summer school. So the most important one for Bayesian deep learning is probably the evidence lower bound. So this quantity is your f of z, and this is your distribution, right? So this appears in variational autoencoders, which you've heard about already, and variational dropout, which will be introduced tomorrow, also Bayesian neural networks, and also pretty much the same problem arises in reinforcement learning, except that maybe R of Z is typically non-differentiable. So you want to optimize your expected reward, and Z in this case is action that you choose. There are also something called natural evolution strategies, which also have this form. But the most important thing I want to point out is that the same problem is studied outside of machine learning for a pretty long time, so maybe since 80s. So in computational finance, this problem is often called sensitivity analysis, and in operation research, it's studied in Q theory. So you can take a look at these two references and just learn about how the same mathematical problem has been studied in different communities. Okay, as a reminder, I want to introduce control variates again, because I want to show how it can be applied to both reinforce and reparameterization gradients. So suppose that we have some function h, some stochastic estimator h, which is correlated with the gradient estimator that we want to use. So I'm not going to talk about some general method for constructing this sort of control variate because it's basically an art. There is no algorithm. Why is that? Because we wanted to have tractable expectation. So we want to compute the expectation analytically. We want to just get the value very cheaply without any sampling, the expected value. But it should be correlated with something for which we don't know the expected value. Because if we know the expected value analytically, we can just compute the derivative for that thing analytically. There is no need in using stochastic approximation. So it's really hard to balance between the two, so the number of control variates we can use generally is fairly limited. Now, suppose that we have this quantity, then we construct a quantity with reduced variance. So this is a new estimator G tilde, which is constructed by taking the original one and subtracting this difference, h minus the expected value of h, times some scalar constant gamma, right? So if you just take the expectation of this thing, you can see that the expectation is the same as expectation of g, because this term's expectation is 0 for any gamma, right? Great. So it's also an unbiased estimator. And we can compute its variance, and it's pretty easy to see that it has this form. And the most important thing is that it's actually a quadratic function in gamma, right? So the optimum value, I hope everyone remembers this formula, it's this divided by this, right? No surprises here, right? What is not appreciated often enough is that if gamma is not optimal, the variance can actually increase. And I want to point out that. So this is what it looks like. So for different h, you will get different parabolas, right? And the optimum is achieved here for this gamma star. But if you overshoot gamma by a lot, you can increase the variance by a lot, right? So it's a pretty big problem. And another thing to notice from this plot is that the higher the correlation between J and H, the larger the decrease in variance, right? So if it's correlated very slightly, there is almost no gap between the original variance and the reduced variance, right? But if it's pretty big, like 0.8, then you get some sizable improvement, right? Okay. Any questions about this? Good. Let's review the reinforce gradient estimator. So one thing I want to point out is that it's often called score function estimator or likelihood ratio estimator. It's all the same thing. It's just that the same thing has been studied in statistics community and many other communities. So people came up with different names for the same thing. And I'm not going to derive this because you have seen this derivation many times. If you want to review it, it's at the end of the slides. But the main idea is you use log derivative trick. You've probably seen it many times already. So this quantity is the stochastic gradient estimator, right? According to the definitions we gave. The thing to notice here is that it does not require gradients of f of z because of just its form. So it's also applicable to, for example, reinforcement learning problems where there is no gradients available because we don't know what is f of z. It's just some black box. But it's usually high variance. So which is why we will discuss control variates for this next. I also wanted to add this little code snippet. That's the only code snippet in the slides, but the reason for that is that you have this formula, but then actually implementing it, you have to scratch your head a bit how to do that. And this is how you do it. You first sample from your queue, and you do stop gradient so that z becomes a constant with respect to your parameters. Then you construct a surrogate loss, which is f of z times q log probability of q. So the derivative of this with respect to phi is exactly this, right? Because f is independent of like any parameters. And then this is the main trick. You construct loss, which is equal to in value to f of z, but its derivative is the same as derivative of surrogate loss. So you do stop gradient. Everyone knows what is, everyone used TensorFlow maybe? Okay, stop gradient just makes the thing have the same value, but 0 gradients with respect to everything, right? So this has 0 gradients, but the value is f of z minus surrogate loss. So you see that the value of all of this is f of z, but the gradient is the same as gradient of surrogate loss, which is what you want. Okay. Now let's take a look at what this actually looks like for some simple distribution. So this is univariate normal distribution, and its log density looks like this. So it's a quadratic function in z. So nothing very scary, right? You all recognize this expression. And in order to construct the reinforced gradient estimator, we just take this log density and differentiate it with respect to mu and sigma, the parameters of our distribution. And then we multiply it by the value of the function f of z, right? So you get something like this. For mu and for sigma, you get this. Okay, any questions about this? Okay, you've probably... Have you seen these expressions yet in the summer school? Have you seen any equations in the summer school? Okay, the important bit of reinforce is control variates, because in practice it typically does not work without control variates. It's just way too high variance. So people have been using baselines like from, I don't know, at least the early 90s. So it's like the most important ingredient to actually make it work. And the baseline that everyone uses is the control variate that everyone uses is called baseline. And it's just this expression, so the derivative of logarithm of your density. And it's very easy to see that it's just the reinforced estimator for a constant function 1. So it's equal 1 for every z, right? Which is, so it approximates this expression, right? And this expectation is equal to 1, obviously. And because of that, the derivative is 0. So the mean value of this thing is 0, which means that it's a control variate with 0 expectation. And because of that, this is unbiased estimator of the derivative. Okay? And now the question is, well, we have that, how do we choose gamma? Now you probably have a little bit more caution about how we should do that, because what everyone does usually is choosing just the approximation of the expected value of f of z, usually by using some sort of running average of f. But the problem with that is obviously it actually can increase your variance. Even if your running average is really, really good, it can still increase your variance. Just because the optimal thing to do is to choose this quantity, and it's a bit harder to do. It's possible, but usually harder. Any questions about this? Okay, great. So you now know that you should do this, and if you're able to do that, you will always at least not hurt your variance, but will probably decrease it. Great. Now let's go to the second method, the main alternative to reinforce, so to say, which is reparameterization gradient estimator. And I'm going to start with the example you have seen several times already in the course. So this is univariate normal distribution. We know how to transform samples of normal distribution with some parameters into samples of standard normal distribution. So normal distribution with 0 mean and unit variance. It's done by this transform, right? So you subtract the mean and divide by sigma. And this gives you epsilon, which is distributed independently of your original parameters. I'm going to call such functions standardization functions, all right? Then we just invert this function and get z equals mu plus sigma epsilon. And from here, you can compute the derivatives of z with respect to mu. So with respect to mu, it's 1, and with respect to sigma, it's epsilon. The most non-standard thing I'm going to do on this slide is to, instead of settling for epsilon, I will replace epsilon with z minus mu over sigma, which is just this equation, right? I'm doing this so that in my gradient estimator, I don't have epsilon. Because I wanted it to only be dependent on z and phi. There is no dependence on epsilon, which is something different. So I'm just using the standardization to plug the value for epsilon. And then the estimator looks like this. So it's derivative of f with respect to z times the derivative of z with respect to the parameter, which is 1 for mu and z minus mu over sigma for sigma. Okay? So one thing I want, some curious historical fact is that actually this was discussed in the same paper which introduced reinforce, like this whole thing. And no one really, I guess, read to that bit of the paper until 2014 or something. So yeah, just read the papers until the end. Okay, now let's take a look at the more general derivation of the same thing. And another thing I want to say is that it's, the same thing is often called pathwise gradients. So if you see something called pathwise gradients, it's probably reparameterization gradient. It's the same thing, but just called in a different way. So we assume that we have a standardization function. So here it's all going to be multivariate, but it's so z is bold because of that. But it's not going to be a big problem for us. So we have a standardization function which maps z to epsilon, which does not depend on parameters. Okay? Then we invert this function, and we perform reparameterization. We just change the variable in our expectation. Okay? So from this, we obtain this. You have probably seen this several times already, right? And then, because this expectation does not depend on phi, we can move the gradient inside. You have probably seen this several times already. So we move it inside, and we get this. And just by using chain rule, we obtain this expression. So it's df over the argument times derivative of inverse standardization function. Okay? And now I want to do last step where I get rid of epsilon in the obtained expression. And I'm just plugging back z. So I'm performing the change of variable back. I'm saying that z is this inverse standardization function, right? So I can, instead of this, get this expression. So I'm just, essentially this is chain rule, right? So you just have derivative of f with respect to the argument times derivative of z with respect to the parameter. The only weird thing here is that this derivative is defined in a slightly scary way. So it's derivative of inverse standardization with respect to parameter at the point epsilon equals standardization function. But you have already seen what it is for normal distributions. You literally take epsilon and replace it with the value of standardization function. It's not actually scary. And so our gradient estimator looks like this. And again, J is just a scalar, and this is a row, and this is a column, right? So it's, you take a dot product basically of two vectors. So it's just chain rule, and the good thing about that is that it fits perfectly into the existing deep learning frameworks. We don't really have to think too hard about the fact that we have something stochastic, because it's just a weird layer which has gradients defined in this way, right? So you basically define the gradient of z using this expression, right? So it's just much easier to use than reinforce. You don't have to write 3 lines of code, you write 1 line of code. But someone has to implement this for you, though. Okay. Now let's discuss when one is better than another. And the standard thinking is that reinforce always has higher variance than reparameterization. And that's like the usual mental picture for everyone. And I want to first convince you on that, and then show that it's not actually true. Okay? So that's going to be the plan. So why would we think that reinforce is always a higher variance? One way to show that is to consider some simple cost functions such as z squared for univariate normal distribution, and then just actually write down the gradient estimators. So for reinforce for mu, it's going to be this. So it's just f of z times this derivative of log density, and it's a third order polynomial in z, right? And for sigma, it's going to be a fourth order polynomial, right? Everyone sees that. So it's z in the power of 4 plus some terms of lower order, okay? For reparameterization, it's going to be a derivative of f times the derivative of z with respect to mu. So here it's 2z times 1, so it's linear. And here it's quadratic. Okay, everyone understands where these equations come from, right? Great. So the standard reasoning is something like that. You see that reinforce is a higher order polynomial, right? So if z is the absolute value of z is greater than 1, then the values of reinforced estimator are going to be much larger than for reparameterization. And because of that, we can assume that it will also have higher variance, okay? So we will get much larger values, and somehow it's intuitive that larger values correspond to a larger variance of the estimator. Okay, and this is what it looks if you actually compute these variances and plot them. So I'm choosing the values of sigma to be 1 and varying mu here. So this is the parameter of the normal distribution. And this is the variance of the stochastic gradient with respect to mu, and this is with respect to sigma. And you see that the top line, which is reinforced without any baselines, is always the worst. The second worst is reinforced with mean baseline, and the reinforced with optimal baseline is, of course, always better than the previous two, but it's still much worse than reparameterization for both of the parameters. And yeah. Any questions about this plot? So have I convinced you that reparameterization is always better? Oh, that's just the plot of y equal of z squared. So it's going to be useful in the next slides. Okay, now let's take a look at a more complex function, which is just exponent of minus kz squared, where k is parameter. And here I'm going to vary k, okay? So what is this function? It looks like this, so this is why this is useful. So for low k, it's bell-shaped. Well, it's always bell-shaped, but for low k, it's very flat. And for high k, it becomes peaky at 0. But it's always between 0 and 1, so it's like unnormalized normal distribution, I guess. Okay? So what happens here? If we look to the left, where it's relatively flat and looking like something like a quadratic function, we see pretty much the same story, right? It's nothing like really surprising here. Reparameterization is better. But as we go to the right, we see that at some point, reparameterization becomes worse than reinforce, even without baselines, which is really surprising, right? But this can happen. This is like actual plot. Another really interesting thing to notice here is on the right plot, so the gradient with respect to sigma, the reinforced with mean baseline is sometimes worse than reinforced without using any baseline, right? So this is actually, we actually see here that for this parameter, it's better not to use a baseline. Whereas here, for mu, it's better to use the baseline. So it's a pretty complicated story, like which baseline you should pick. So it's always better to pick the optimal one if you're not sure, but it's hard. Yep. Sorry? Oh, the parameter is k, which is this parameter of the cost function. Sorry? Oh, yeah. So in the previous slide, I basically didn't have such parameters, so instead I varied mu of this quantity, and here I'm varying k, which is this quantity. So Yes, I just didn't have a parameter in my cost function, and here I do have, so I'm varying that. Okay, so why does this happen? So my best intuition is the following. So the values of this function are always bounded between 0 and 1, right? So its variance cannot be like too high. Whereas if you look at the derivative of this function, as you increase k, the derivative becomes really large around here, right? So the absolute value of your derivative becomes large. And somehow this corresponds to large variance for reparameterization. Okay? So the story here, the intuition here is that if your cost function is really badly behaved, like it's very wiggly, then probably reparameterization is not going to help you too much. So yeah, and on the other hand, is if it's very smooth, and an example of smooth function is, for example, when you're doing something like evidence lower bound. It's usually very smooth and nice. So then probably reparameterization is going to help you by a lot. This is just another example of this intuition. So this is cosine of kz. So when k is really small, it again behaves like this sort of almost quadratic function. And when it's large, the function becomes very wiggly, so it jumps a lot. And you see pretty much the same story, except that here for high k, it does not really matter which baseline you use for reinforce. It always works roughly the same. And again, there is some region where the mean baseline actually hurts compared to using the standard reinforce. Okay, any questions about this? Okay. Well, we probably care about cosine, don't really care about cosine functions, just an example of function which is like multimodal and things like that. So it's not just an illustrative example. I guess the technical reason is that for cosine function, you can compute this variance. So it's all analytically computed variance. And if you choose a more interesting one, then you will probably not be able to do that. So, okay. So what are the issues of reparameterization gradients, which we probably want to use for, at least in Bayesian deep learning? One big limitation is that it's not applicable to discrete distributions. And this was discussed during the discrete latent variables lecture on Tuesday. So I'm not really going to talk about that. But the short version is that you should use some relaxation method, which turns that into the discrete latent variables into continuous ones. Another issue is limited scope of applicability. In the way I described this, reparameterization is only applicable to distributions which have simple inverse of the standardization function. And that's not all the distribution out there. And the last point is that the variance of the estimator may be high, as we saw. So maybe we want to use control variates for reparameterization, and I will discuss how we can construct such an control variate. Okay, so now we're talking about expanding the applicability of reparameterization. And this is one example of distribution which is hard to reparameterize. This is so-called von Mises distribution. It's a distribution over angles, or in other words, directions. So its domain is from -pi to pi. And it looks somewhat similar to normal distribution. When the parameter kappa, which is something similar to inverse variance, it's called concentration, is low. So it becomes basically a normal distribution. But as you decrease the concentration, it tends to uniform distribution over the circle. Okay? So it's some sort of distribution which can interpolate between something close to normal and uniform distribution on a circle. It has two parameters. Kappa is concentration, and mu is the location, which just shifts everything on your circle. And mu is very easy to handle in terms of reparameterization because you just sample from von Mises with 0 mean, and then you just add that mean. So it's pretty simple. And kappa is the hard parameter here. This is gamma distribution. So it's a very important distribution in probabilistic modeling. It's conjugate prior for normal, and you can also obtain many, many distributions from gamma. And again, it has two parameters, alpha and beta, and the beta parameter is the simple one to reparameterize because you can sample from gamma with beta equals 1 and then divide by beta, and this gives you the necessary value. And alpha is the tough parameter, which basically determines the shape of this distribution. Assuming that we have managed to reparameterize gamma, we can also reparameterize many other distributions, and maybe the most important of them is Dirichlet distribution, which is a sparse distribution on simplex. So its values are inside a unit simplex, so they sum to 1 and they are greater than 0. And yeah, the density looks like this. So by sparse, I mean that it has peaks at the corners of the simplex. So it prefers values to be close to the corners, assuming the parameters are set are less than 1, I guess. Yeah. So how can we sample from Dirichlet? One way to do that is you sample one gamma distribution for every parameter, and then you just normalize them this way. So then, just by using chain rule, assuming that we know derivative of t with respect to alpha, we can backpropagate from z to alpha. Okay? So that's like the idea of why, if we want to reparameterize Dirichlet, we want to first handle gamma. Great. The first method I want to discuss is generalized reparameterization gradients. The motivation for this method comes from the following idea. Let's say that we cannot compute dz over d phi for our target distribution q phi of z. It's just too hard for us. For example, it's a gamma distribution. But for some reason, we have another distribution r phi of z, which looks really, really similar to our distribution. So it's really, really close, but it's a different distribution. So the most naive thing we can do is just take dz over d phi for that distribution, which I'm going to denote ur, and just use that in place of the correct dz over d phi. So it may work, or it may not work. We don't really know. It's going to be introduced bias into our gradients, and we want to avoid that. And we can avoid that by adding an additional correction term, which looks like this. So it's a derivative with respect to phi of log of ratio of the densities of Q and R. Okay? So because we expect this ratio to be very close to 1 most of the time, this log is going to be very close to 0 most of the time, and probably the derivative is also going to be very close to 0. So it is expected to work if Q and R are really similar. So yeah, this is the gradient estimator for generalized reparameterization. The first term is similar to reinforce, so it's also derived using log derivative trick. Again, I'm not going to derive that, but there is a slide at the end. You can take a look if you're interested. And this is the reparameterization gradient for a different distribution R phi. So notice that we sample from Q, but the reparameterization gradient is computed for R. Okay? So the samples come from the right distribution, but the reparameterization gradient is computed for a wrong distribution, which is why we need the correction term. There is another view of this expression, which is that it's reinforced. So notice this part, right? So the nominator of log, right? This is just reinforce. So everything else can be interpreted as control variate, right? So that's another view, which, yeah, somehow I find it a bit hard to process, but it's definitely correct. Okay, now the big question is how do we choose R, right? And there are two papers, and they actually differ mainly in how they choose R distribution, the approximating distribution. The first idea is that, well, so we know that for normal distribution, it's basically defined by its first two moments, right? So, but other distributions are not like that. So what we can try to do is to standardize the first and second moments, basically do kind of the same thing we did for normal. Okay, so we apply some standardization, which makes the mean 0 and variance 1. But if it's something like gamma, it also has higher moments, which are also depend on the parameter. And because of that, it's not going to be perfect. It's not going to be like the same distribution for any parameter. It's going to be slightly different. And basically, the reinforced term will make the correction for this discrepancy. All right? So again, if the standardization would be perfect, then all of these densities would be the same, right? Because that's what means that the standardization removes the parameters from our distribution, right? Here they are slightly different. So it removes most of the parameters, but not all of them, not all the dependents. Okay, any questions about this? I feel like Okay. So this is called the generalized reparameterization gradient. So you produce R by, the distribution is defined by this partial standardization, basically. You just apply the change of variable formula, and you get the density for R from here. This is another idea called reparameterization gradients through acceptance rejection algorithms. And the idea here is that, well, when you do something like, when you try to sample, for example, gamma distribution in NumPy or something else, there is actually some method which produces samples for you. And this method is, most of the time, a rejection sampling method. And these algorithms have been studied for decades, and basically the whole goal of the field is to construct an approximating distribution, which is, first of all, easy to evaluate, so it's easy to sample from it and easy to obtain density. And secondly, it approximates the target distribution really, really well, because the better the approximation, the higher the acceptance rate, which means it just runs faster. So the whole field was constructing this sort of approximations. And this is one of the approximations. So this is the rejection sampling proposal for gamma. So you see that it matches the actual gamma really, really well. And as I said, it's usually a simple transformation of uniform or normal random variable, so it's easy to compute the density. Again, using the just the change of density under change of variable in density formula, right? Okay, so that's the idea. Also, this paper has a really nice trick called shape augmentation for gamma. So what they notice is that these rejection sampling proposals become exact for large alpha. So they just coincide with the actual distribution you want, right? So the idea here is very neat. Instead of reparameterizing gamma with parameter alpha, you will instead sample and reparameterize distribution with parameter alpha plus b, where b is some integer called shape augmentation parameter. For example, you can take b equals 10. And then there is a property of gamma distribution which says that you can reduce the parameter of gamma by 1 by sampling a uniform random variable and multiplying z by this quantity, u in the power 1 over alpha. So this allows to reduce the parameter by 1 of your sample. If you do this b times, you obtain the gamma alpha 1 distribution sample, right? But you only need to reparameterize this distribution, which should be much easier, okay? So that's the idea of shape augmentation trick. Unfortunately, I don't know about application of this to other distributions, so I'm not sure how generally applicable this is, but for gamma, this is definitely one thing you could do. Okay, so here are the results, and on the left you see a synthetic problem, which is estimation of gradient of cross entropy. So it's basically a synthetic problem where you can compute the expectation analytically, and then it's easy to compute the variances. On the top you see, the distribution here is Dirichlet with one free parameter, which is variate. And alpha is this parameter, so you compute the variance in different points. On the top you see the blue line, which is generalized reparameterization gradient, and it has fairly large variance. Rejection sampling, variational inference, which is all these lines. So they call it rejection sampling variational inference, even though it can be used not just for variational inference, but so I'm going to call it rejection sampling reparameterization, but they call it RSVI, rejection sampling variational inference. So B here is the shape augmentation parameter, and you see that for B equals 0, it's basically the same thing, but as you increase B, the variance decreases by a lot, by orders of magnitude, actually by 4 orders of magnitude. So that's a lot. And the cost you have to pay is 10 samples of uniform distribution per sample of gamma random variable. On the right, you see a training of generative model of images. So on x-axis is the time in log scale, and on y is the evidence lower bound. And you see that rejection sampling reparameterization trains pretty fast, whereas reinforced with control variates is very slow to converge, and generalized reparameterization is a bit slower than RSVI. So I guess it's interesting to see that all of them converge to the same thing. But if you're switching, for example, from generalized reparameterization to rejection sampling reparameterization, you just get something reasonable much, much faster, right? So this is one of the advantages you will almost definitely see from reducing the variance of the gradients. You will not always see improved results, but almost all the time you will see that your model trains faster. Okay. Any questions now? Let's have a 5 minutes break. Yeah. Okay. Sorry, could you repeat? Okay, so yeah. So the question is whether other control variates have been applied. So specifically the ones used in importance sampling. So I'm not so sure, unfortunately. I know that one of the things people do, for example, in natural evolution strategies, people do antithetic sampling. So antithetic sampling is something used in statistics community which has been applied, but it's not really a control variate. It's something different. Yeah. So regarding control variates, I'm not sure, but I'm sure there is like lots of things which could be applied, and they will probably work. So, any more questions?
Thank you. So we're talking about one-dimensional case, and it was stated in the slide 1. And is extending it to multiple parameters change anything?
Right. No, it doesn't. The reason for that is that you just, if you want to consider the multiple parameters, you just do the same thing for all of the parameters. And for example, for reparameterization, you just compute the derivative of f once, and then you just multiply it by different derivatives of z with respect to parameters for each one of them. So it was just mostly the question of keeping the notation simple. So you can write everything down very easily for multiple parameters and ones, but you don't really gain anything conceptually, but the notation becomes harder. So yeah, it's very straightforward.
So you mentioned a method which gives most of the time better convergence speed. So could you please tell what control variates you use for that method? As far as I see, it's reinforced, plain reinforced, right? It gives higher convergence speed on the last slide, at least. So could you please give more details about control variates which you used for this fastest convergent method?
Okay, first of all, just a disclaimer. I'm not talking here about my own work. So this is work by all these people. And so the fastest converging one here is rejection sampling reparameterization. And I guess this is called black box variational inference, which is reinforced with I think the control variate there is fairly simple, so it's basically, it's trying to approximate the mean, but they also do something called Raoub equalization, which is another way to reduce the variance by analytically taking the expectation of some of the variables. Okay, I don't have too much experience with reinforce, and I would just advise to first try doing the mean and hope that it works. So but there are things such as Raoub equalization which can be used jointly to further reduce the variance. It's just that I don't want to talk about absolutely everything. Okay, now I'm going to talk about implicit reparameterization gradients, which is an alternative method of handling reparameterization of these hard distributions. This is our joint work, my joint work with Shakir Mohammed and Andrei Mnih. And the motivation for this work comes from the following fact. For univariate continuous distributions, we can take the cumulative density function, CDF, which is defined like this. And one of the simple properties from statistics is that if you plug the random variable into the CDF, the resulting random variable is uniformly distributed. Does everyone remember something similar to that? Okay, good. And this means that CDF is a standardization function for univariate distribution. Well, univariate continuous distribution, because we also want this to be smooth. For discrete, it's not going to be as easy. But the problem is that computing the inverse of CDF and computing the derivative of inverse is really hard. As an example, here's the CDF of gamma distribution. It's defined like this. So this is just the density of gamma, and you integrate it from 0 to z, right? The problem is that this integral is intractable, so you cannot compute it analytically. And because of that, it's really hard to invert it. So if you want to compute this thing, you typically use something like Taylor series or continued fraction expansion. But inverting it is really hard. So typically what you do is root finding iterative methods, which is really slow because it has to compute the value multiple times. And when you have computed this inverse, you also want to take the derivative in order to compute the reparameterization gradient. And derivative of the inverse you can technically do by something like finite difference, but it's going to have really poor precision. Yeah, a question? So the question is, can you invert the derivative? Well, no, because it's a different thing. We need the derivative of the inverse, and you cannot really commute inverting something and taking derivative, right? It's so okay, let's return to that maybe on the next slide. So the question is, can we avoid it by using some simple calculus? And surprisingly, the answer is yes, if we do something called implicit differentiation, which is typically studied during the maybe first 2 years of undergrad, but somehow people often forget this thing. Well, I definitely forgot that it exists. So what is implicit function? Probably most of you heard about this. It's just something like this. It's basically a function which defines relation between tuples of numbers, right? So here we can say that a tuple which satisfies this defines an implicit function. So we can think of this, for example, as a function of y. This defines some function y of x and phi. To make this well posed, let's say that x and y is greater than 1. And the question is, what is derivative of y with respect to phi? This is what we want to find. And obviously, if you just plot this in xy plane, it's just like a quarter of a circle, right? With radius defined by phi. So the explicit differentiation approach is you first express y as a function of phi and x, right? Which is this. And then you differentiate with respect to phi, which gives this, right? No surprises here. So this is what you would typically do. But you can instead do implicit differentiation. So this is the only time we will use total derivative. Does anyone remember what is total derivative and how it's different from partial? So yeah, so the total derivative basically computes how everything, so it computes the derivative over all possible paths, right? Whereas partial derivative assumes that all other variables are fixed. So here, y, we assume that it's a function of phi, so which is why we need to expand it like this, right, on the left-hand side. On the other hand, we assume that x is independent, so its derivative is going to be 0. And on the right-hand side, we're going to get just 1, okay? And when we have done this, we can just express the partial derivative of y with respect to phi by using super simple algebra, just by dividing this by 2y. And we get this equality. And the amazing thing is that it turns out we didn't even need to know x in the first place, right? Of course, this is just the same as this, but it's just a different expression which is much easier to compute in some cases. Like here it does not matter, but it will matter on the next slide. Okay, everyone kind of remembers what is implicit differentiation. Okay. Let's take a look at how we can apply this to reparameterization gradients. So this is standardization function S phi of z that maps samples of z to epsilon. We will assume that z is essentially an implicit function of epsilon and phi. And we are interested in finding the derivative of z with respect to phi. Okay? So now we're going to take the total derivative of both parts with respect to phi. Now the left-hand side depends on phi in two ways. What are these ways? Yeah, well, through z and directly through this parameter. So, and because of that, the left-hand side is expanded like this. It has two terms. And this is where the distinction between partial and total derivative becomes important, right? On the right-hand side, we get just 0 because we assume that epsilon is independent function. We know that its distribution is independent on phi as well, just because of definition of standardization function. From here, we can express derivative of z with respect to phi using, again, simple algebra. Except here, because I said that z is going to be a vector, we are now having some matrices. So this is inverse of the Jacobian. There is a minus sign. Yeah, and so this is inverse Jacobian of standardization function with respect to z, and this is the derivative of standardization function with respect to phi. All right? So this is a vector, this is a matrix, and this is also a vector. Okay, so just to make sure we're on the same page, this is the same derivative as what we computed originally. So this is the same dz over d phi as in the standard reparameterization. Okay? It's just computed in a more tractable way. Okay, great. Now let's see how we can apply this. As I already said, for univariate distributions, we can just always use the cumulative density function. So because it maps samples of z to samples of uniform random variable, right? So if we plug this standardization function into this expression, what happens? So what's the derivative of CDF with respect to z? It's the density, right? Because CDF, I don't have it on this page. Yeah, it's the derivative with respect to the upper limit, right? So it's just the value in the upper limit. So it's the density. We invert this density, multiply it by this, so this is going to become derivative of CDF, and take a minus sign, which is precisely what you see on this slide. Okay, no magic here, it's just simple transformation. Now, the hard part about this expression is the second term, derivative of CDF with respect to phi. It's definitely easier than derivative of inverse CDF, but it's still a bit tricky because it's typically not implemented in standard libraries. But the good thing is that if you actually take a look at how this is computed, usually it does something like Taylor series. And you can just take that code and perform automatic differentiation of that code. So with respect to the parameter phi. And it will give you the necessary derivative, right? So this is what we're going to do. Okay, so for multivariate case, it's also reasonably simple. So you can look at this distribution, this random variable z, as a sequence of conditional distributions. So I think it's called ancestral sampling most of the time, right? So you can first sample z1, then z1 given z2 given z1, etc. Every time you condition on all previously generated things. It's just the same expression, it's the same distribution, but written in a different way. But the good thing, on every step, you just need to sample from univariate distribution. And for univariate distributions, we know that we can use the CDF. So we just apply CDF to each one of those, and this naturally gives you a vector of independent uniform random variables. Okay? So you don't have to sample this way, it's just a way to compute the standardization function. Okay. So what are the applications? which can be handled by implicit reparameterization gradients. So for these kinds of distributions, we can just apply this formula and get the derivative. You can also do this for all of the next ones, such as inverse gamma, beta, Dirichlet, but it's just much easier to write them down as transformation of gamma samples, just because you won't have to compute the complicated distributional transforms in this case. The really good news here is that for most of these distributions, you don't really have to code up anything because they are already implemented in TensorFlow distributions and in the great library called TensorFlow probability. So you just take these classes, you sample from these distributions, and the samples will be differentiable with respect to the parameters. So you can just plug them into your model. You don't have to do anything else, and the derivatives will be computed for you. So, and maybe a bit more generally, if you want to find an implementation of something which was discussed during this summer school, one of the things you can look is TensorFlow probability library because it has really good implementations of many, many algorithms related to Bayesian deep learning. Great. Now, let's talk about how well implicit reparameterization works. And the first thing is to check whether the automatic differentiation approach actually works well. And the main alternative is to just approximate the derivative using finite difference, right? So instead of doing this automatic differentiation, you can compute your function in 2 points, take their difference, and multiply by, and divide by the step size, right? So the centered finite difference. You see that both of them work, but the automatic differentiation gives a much better error. So the error is much, much lower, many orders of magnitude lower, which is not really surprising because the because finite difference loses a lot of precision. But their running time is roughly comparable, mostly because it's for automatic differentiation, the computational cost is typically twice the cost of the original computation. So it's roughly the same thing in terms of computational time. You can also do something like approximate explicit reparameterization, which what David Knowles did in 2015. And it basically does this. So it computes the inverse CDF and then performs finite difference approximation to the derivative. It works, but it gives you really poor error, and it's also very slow. So it's slow because it has to compute the inverse CDF, and the error is not really great because sometimes the inverse CDF method just does not converge right. And then you get like really bad approximation of the derivative. Okay. Oh, yeah. So, okay, any questions about this page, about this slide? Great. So, yeah, and this works for gamma and von Mises alike, so it's, yeah. I think it's pretty general, so you can apply it to many univariate distributions. So this is a slide on related work, and maybe one thing I want to point out is that I found a paper from 1988 which proposes both implicit and the standard reparameterization, but they considered absolutely different problems on Q in theory. And it was pretty surprising. Basically, I thought this was something reasonably novel and very interesting, but then it turns out that there is a paper written before I was even born, which proposed pretty much the same solution. There have been several papers in machine learning which did something similar, so they did not really, it wasn't really the main focus of the paper most of the time, or they didn't want to consider all the distributions. But this paper actually did something very similar. It's a paper from Jankovic and Obermeyer published at ICML 2018. And for gamma distribution, they do pretty much the same thing, except they compute the derivative of CDF in a very different way. So they do some sort of analytical approximation. And their method has been implemented for gamma in PyTorch. So you can also take a look at this. Yeah, and compared to all these works, we did some interesting thing. I guess the most interesting one is that we generalized this to arbitrary standardization functions and multivariate case, which hasn't been done before somehow. And also we provide this method, we propose to do automatic differentiation for CDF derivative, which seems to be very easy to implement on one hand and work really well on the other hand. Okay, here are some experimental results. This is the same problem which was considered a couple of slides ago for rejection sampling variational inference. So basically, I just re-implemented it and tried my own method. So this is cross entropy of Q and P, where Q and P are Dirichlet distributions. And what happens here is it's a 100-dimensional Dirichlet distribution, and all the parameters are the same except for this first parameter. We're varying this parameter, okay? And the optimal value is 2. And we're measuring the variance of the gradients with respect to phi. So we see that as we increase B, the variance of RSVI decreases, but implicit reparameterization already gives you the best variance without actually having to sample any additional uniform random variables or doing something like that. So because of that, it's also a bit faster. And the same thing holds for von Mises distribution. So it's basically a similar problem, but with von Mises. And for von Mises distribution, as I said, I don't know of a shape augmentation trick for von Mises. So I didn't know how we can improve on RSVI by doing something like shape augmentation trick. And because of that, RSVI is just, there is no way to decrease the variance by doing something. So it's always worse by about 1.5 order of magnitudes. As an application, let's consider latent Dirichlet allocation. Okay, who heard of latent Dirichlet allocation? Wow, okay, almost everyone. So it's a fairly popular topic model, maybe not right now, but maybe 10 years ago. So it's a topic model for documents represented as a bag of words. So what this means, you take your documents, for example, messages on a forum, or like in Facebook, and you represent it just as counts of how many number of times each word occurred in this particular post, okay? So it's just like vector of numbers. And your goal is to find topics, and topics basically mean that each document should be assigned to one of the topics, where topic is distribution of words. So depending on which topic you are in, you will most likely choose different words, essentially. So it's written down using this pretty simple probabilistic model. So the prior is Dirichlet, and this captures the fact that we want it to be sparse. So we want every document to correspond to usually just one topic, maybe to 2, but not to all of them. And this is our likelihood. We have a linear decoder, which means that we take our topic vector theta and multiply it by a matrix phi, which gives the distribution over words for this particular document. And then we independently sample each word from this categorical distribution. Okay? So the main goal is to find this topics matrix, words times topics, and each topic should be normalized over words. So it should be a distribution of words. The standard approach to this problem is called stochastic variational inference, and it's relatively, so you have to derive some formulas, you have to code it up, but now that we have reparameterization for Dirichlet, why won't we do black box amortized inference, which is just a fancy way of saying that we want to do the same thing as in variational autoencoder. So we're going to say that here's our approximate posterior or encoder, which looks at the back of words and produces the vector of topics, okay? And it's going to be a Dirichlet distribution parameterized by a neural network, okay? Then we will write down the evidence lower bound, just as in variational autoencoder, and optimize it using implicit reparameterization gradient. Again, just as in variational autoencoder, except that now we have to use implicit reparameterization gradient because we have a Dirichlet distribution we sample from. As an alternative, as a baseline, we use logistic normal LDA, which is what people typically did before, which is just replacing the normal, the Dirichlet distribution, which is hard to work with some distribution which is easy to work with. And in this particular case, it was logistic normal distribution, which is sample from normal, multivariate normal, and apply softmax. Okay? So it's basically also distribution on simplex, but a different one. Yep. Well, I mean, hard to work with, I just mean that it's hard to compute the reparameterization gradient. So that's what I mean. So this method also allows to do something like variational encoder, right? Whereas original LDA formulation, you actually have to backpropagate through samples of Dirichlet. So that's what I mean. I'm not saying that it's a bad distribution. It's a really good distribution. So here it's actually very simple because you just, for sampling, you just sample from normal and apply softmax. And for KL divergence, actually, these softmaxes just cancel out, and you just need the KL between normals. So it's like really easy. But the main problem with logistic normal in this case is that Dirichlet is actually sparse. You saw this picture. It has peaks of density in corners. Whereas logistic normal, it does not really have peaks in the corners. It has peaks close to the corners. So it's not sparse, it's like almost sparse. And we will see how this will play a role later on. So it just has a bit different properties. So here are some results. So this is test perplexity, and lower is better. So it's essentially something like log likelihood, but normalized in an interesting way. But the important thing is that it's like just you want it to be as slow as possible. So we compare implicit reparameterization with RSVI again. And what we see is basically the same story we saw on the synthetic example, except that now we need to choose B, which is larger. So previously it was enough to choose B something like 10. Now we need to choose B equals 20 in order to match the performance of implicit reparameterization. So it kind of makes intuitive sense that the harder your problem is, the larger you have to do this shape augmentation to make it work really well. The good news is for implicit reparameterization, you don't need to tune this additional hyperparameter. Very surprising thing is that stochastic variational inference, the standard method, seems to work worse. I don't have an extremely good explanation for that. It's probably got to do something with local optima, but that's like saying, yeah, that's just, you know, you can say this about any problem in deep learning. It's got to be with local optimas. For some reason, SVI works a bit worse, even though it does not use amortization. So technically, it should be better, but in this case, it's worse. Maybe because we're running SVI for a limited number of steps, so the approximation it comes up with is worse than what you get from the encoder. Maybe that's the reason. And LN-LDA, logistic normal LDA, works the same on 20 newsgroups, but a bit worse on RCV1. On the bottom, you see training curves, and you see that basically the same thing. So the variance for RSVI matches the variance of implicit reparameterization for B equals 20, and it's way higher for lower B. And this corresponds to faster training. So the lower your variance, the faster you train. So same story as before. Now, I promised to say that there is a problem with logistic normal, and it's not a sparse distribution. So here we can visualize the obtained topic weights. So for implicit, for LDA, actually some of the weights go to 0, so you're not using these topics at all. Whereas for LN-LDA, all the topics are used, even if they're not really necessary. And this occurs on both data sets. So RCV1 is a more complex one, and you see that LDA is using more topics, right? And also for, we can see that for LN-LDA, the topics are usually less informative. So it just copies the same topic over and over again, because it's basically not sparse. It just, for some reason, wants to copy the same topic, and it's preferable for it. Whereas LDA actually prefers to use sparse topics. So they are, each one of them encodes something different. Oh, and one last thing is that the code for this example, for the LDA example, is available in TensorFlow probability. So if for some reason you want to do a topic modeling using LDA of your dataset, you can download it and play with it. This is another example, variation autoencoder. So you may have seen that during this summer school, we mostly talked about variation autoencoders with normal, prior, and posterior. But now we can do other things as well. So this is embeddings, so the latent spaces learned for normal, prior, and posterior. And this basically means that your latent space is the whole real plane. So it's 2D, so R2 plane. And it should concentrate around the center just because of how normal prior works, right? On the other hand, we can try something different. So here we're doing uniform prior and beta posterior over unit square, which is different. And we see a very different behavior. It's not trying to squeeze everything in the middle, but instead, somehow there is something interesting going on around the corner. So you see that somehow the corner looks a bit qualitatively different than the center. On the right, we see the most interesting example, at least for me, which is uniform prior and von Mises posterior over this distribution. So who can guess what is the topology of this latent space? So I also thought it was a sphere, but then I realized it's actually a donut, so it's a torus. So donut-shaped thing, right? Because these two von Mises are independent. So because of that, it becomes a torus, 2D torus. And you see that this is, so the left row is the same as the right row, and bottom is the same as top. So it's like wrapped around left, right, and top, bottom. Okay? So the bottom line here is, if you have prior knowledge about your data set, you know that the latent factors are bounded, for example. Then you probably want to use something like beta posterior, because then your latents will be bounded. If you have prior knowledge that they should encode direction, maybe you should try doing von Mises posterior, because then it will correspond to something circular. And these are the training curves for for von Mises, and again, it's basically the same story as for the synthetic problem. The variance for RSVI is higher, and this corresponds to slower training. So you just have to wait for a longer time to get the same performance for RSVI. Okay, great. Finally, I'm going to talk about how we can reduce the variance of the reparameterization gradient. And this is the paper called Pathwise Derivatives for Multivariate Distributions. The first thing I want to point out, I'm not going to prove it, but you will have to take my word for it. So for univariate distributions, the reparameterization gradients are unique. And intuitively, this is because you can transform one standardization function, like any standardization function, into the CDF of that distribution. And this transformation will not affect the value of dz over d phi. Of course, the same applies to factorized multivariate, because those are just products of independent univariate distributions. But for multivariate distributions, which are not factorized, it's not the case. And we will now see an example. Let's recall what happens to multivariate normal distribution when we linearly transform it. So you probably remember this formula. Is anyone confused by this formula? So when we multiply normal distribution, so this is d-dimensional normal distribution, standard normal. We multiply it by matrix A. The covariance becomes A times A transpose. And the mean, I'm just always assuming that it's 0. Okay? So the mean is going to be 0 everywhere. So the standard thing that you can do in order to reparameterize multivariate normal with 0 mean is you start from saying that your covariance matrix is going to be defined in this way. So this is Kalecki decomposition. So L is a lower triangular matrix. And we know that any positive definite matrix can be written down in this way. So you will just say, well, my L of phi is my parameter. So L is my parameter, and phi is maybe one of the elements of that matrix. Okay? So that's an easy way to parameterize covariance matrices. And this is what people actually do when they want to work with multivariate normal. Okay. Then for this distribution, we can write down some reparameterization. So one way is to multiply L by standard normal noise, right? Because L times L transpose is sigma. It's written here. So this will give the right distribution for us. Okay? And here I'm just writing down the reparameterization gradient for this transformation. So when we differentiate with respect to phi, only L will depend on phi. So we get this, and then we plug back the expression for epsilon, which is from here, L inverse Z. Okay, from these lines I will remove the dependence on phi. We'll just keep it in mind, because otherwise the expressions become just too large. Yes? So this is derivative of L with respect to phi. So yeah, I'm assuming that this is like a matrix valid function of phi, something like that. Okay, what are the alternatives that we can do? Actually, it's pretty easy to show. You can try this, doing this yourself, that all linear inverse standardizations, so like valid transformations, for multivariate normal have the following form. You take this L and multiply it by an orthogonal matrix. An orthogonal matrix is the same as rotation matrix. So it satisfies this, and it corresponds to rotations of the space. So the intuitive picture here is that if you take Q times epsilon, you just rotate epsilon, right? And its distribution is the same, standard normals. So it's pretty easy to see that this whole thing has the right distribution, the one we want. So this is formally written down here. Now, what is the reparameterization, so dz over d phi look like for this transformation? Surprisingly, it's different. And in order to show that, we will need a property of orthogonal matrices depending on parameters. So the derivative of Q, which is orthogonal, is equal to S times Q. And S is skew-symmetric matrix. So at the end, there is a slide with an example, or you can try proving that. It's actually pretty simple. It's proven by starting from the definition of orthogonal matrix. You take a derivative, and then you can express the derivative of Q from there. And it will be of this form. Now, let's compute dz over d phi. So again, it's derivative of LQ times epsilon, right? And then we will just use the formula for derivative of product of two things, which is this, right? Then we will use the property I just showed and plug the expression for derivative of Q. And we will get this. Now, we're plugging back the expression for epsilon. And we get this. Okay? The great thing about this is that then Q's just cancel out. So this Q goes away and this Q goes away. And you get sum of two terms. Do you remember one of these terms from previous slides? Yeah, the first one is the same, but the second one is different. Yeah, the L is the same, everything is the same. So we just obtained a different dz over d phi, which is also valid. So it's pretty surprising, right? So this is shown on this slide. So we have obtained two unbiased gradient estimators for the same thing. One of these looks like that. This is for z equals L epsilon. And this is for this z equals LQ epsilon. We get this one. And what this means is that we can now take a difference of these two, and we see that this quantity is a control variate which has zero mean, right? So, and this holds for any f of z and any skew-symmetric matrix S. So S cannot be any matrix, it has to be skew-symmetric matrix, but it can also depend on the same quantity phi, right? And we can optimize S to minimize the variance of the stochastic gradient. So I'm not going to go into detail, but in this paper it's done using the same rebar trick as you have heard already on Tuesday. Sorry? Oh, the skew-symmetric matrix is just this. So it's like almost, so if there would be a plus, it would be a symmetric matrix. But for skew-symmetric, when you take a transpose, you also have to take a minus sign. So that's the skew-symmetric matrix. So here are some results from the paper. So they are doing Gaussian process regression, and they are comparing three different ways of computing the gradient for this multivariate normal distribution with full covariance matrix. The first one is RT, standard reparameterization, so the red one. OMT is a previous paper by the same authors, the same first author, which just picks Q, which is optimal for identity function. So it's not optimal for other functions, but for identity function, it's simple to compute. So wait, no, it's not. It's actually expensive to compute, but it's analytical. And AVF is the control variate I just described. And here they have a parameter called M, which essentially denotes how many parameters S have, because you can parameterize Q-symmetric matrix using in many different ways, and they have a parameter which denotes how many parameters you have there. And you see that in terms of both the number of iterations and walk log time, using this AVF, adaptive velocity fields, actually helps you achieve better results. Okay. To conclude, I hope I convinced you that stochastic gradient estimation is a general and important problem. And we have two methods, the two main methods, which are reparameterization gradients and reinforce. And the first one works better when the cost functions are well behaved, which is pretty often the case. Reparameterization can be applied to many continuous distributions. And we studied two methods, generalized reparameterization and implicit reparameterization. And implicit reparameterizations usually have lower variance, and they are also implemented in TensorFlow for many distributions, so it should be pretty straightforward to use. And finally, reparameterization for multivariate distributions is not unique, and by exploiting this fact, you can get a very interesting control variate for multivariate normal distribution. Okay, that's it. Thank you. Any questions? So I guess we have about 4 minutes for questions, and then we should just probably stop, and I can answer any questions after that as well. Yeah.
Yeah, thanks for the great talk. Now with a mic, thanks for the great talk. I was curious, so are there any distributions, sort of continuous distributions left for this generation of researchers to be reparameterized? Like, what doesn't work currently?
So one of the things which I think does not work is when you have areas with zero density. So like you could imagine distribution so which goes to zero somewhere in between. It's actually essentially this becomes a discrete distribution in some sense. So this one is hard to work with. I know of one paper which tries to handle that, but it's very tricky, basically. And the reason for that is that in that case, you cannot that easily move the derivative inside the integral in any of the methods. So it becomes hard.
Thank you.
Yeah, and another thing is that maybe we should just work more on control variates for multivariate things, because we don't use multivariate things too often right now. Maybe one of the reasons is that they are just a bit tricky due to high variance. Yep.
Such a question. Thank you for a nice presentation. The question is as follows. In statistics, when you do sensitivity analysis, you usually check whether the results are significant. When you see some improvement, can you do this significance analysis here?
Wait, you mean by significance? Do you mean the significance of like the experimental results or significance?
Yeah, I mean you show a lot of experiments. You see the curve of elbow is slightly higher, but this is significantly higher. Or just
well, I mean. In machine learning, people typically do something like, so there are like error bars, so you basically run this thing 5 times and report the standard deviation, and then like if they don't intersect, then it's probably significant. So yeah, sometimes people do something like t-test or something like that yeah. Yes, so in that particular table, what was the case is that implicit reparameterization was significantly better than the LNLDA thing, but this not significantly better, it was the same as the RSVI, so which was something we expected, basically, for a high enough B, of course. Yeah, and I guess for maybe tables like this one, you don't really write down the standard deviations because you can just repeat this many, many times and you say that your standard deviation is really low. So that's, but that's just an experiment which you can run on your computer, so you can just repeat it like 10,000 times. So there is not really a deviation. Okay, I guess we're out of time. Thank you.